Greetings, math friends. We are going to look at some basic properties for logarithms. These are functions that typically are uncomfortable or confusing to students, but we need to think about them as a function like any other function. They have properties and they have specific behaviors. The first thing that I want to do is just introduce form. A logarithm is going to have the word log, that's the name of the function, and it's going to have a base value. This is the base system that it's going to operate in. This could be a variety of numbers. We're going to start with 2, a binary system, that's the base. It's a subscript on the log. And then the number, which is going to be the input value into this function. Let's say 4. If this is our log base 2 operating on 4, we can have parentheses around here, and this is reminiscent of f of x. Instead of a generic f, we have a name for our function called the log, and this is the thing that we're operating on. If we knew what x was, we would place 4 into here, and we would have f of 4. In this case, we have log of 4, and we know that this is equal to some other real number value, say a. Just as we can say that f of x is equal to some value, we can say that log of x is equal to some value. Logarithms were developed over a period of about 100 years, from the time that the first paper was published until we get them in their modern form. So it took a while to develop logarithms. It may take you a little bit of time to get used to all the properties of these special functions. One of the properties of the modern logarithm is that the log for any valid base operating on 1 here is going to give us a return of 0. So you can know, regardless of what your base is, if you have log base 2 of 1, this is 0. If you have log base 10 of 1, this is also 0. It doesn't matter what the base is. If you're taking the log of 1, you get 0. The next thing that I want to talk about is the buttons that are typically found on scientific calculators. You typically have these 2 buttons, which are logarithms, and some calculators may have other functions available, but these are the 2 basics. This is the natural logarithm. This is base e. This is the number e. This is like pi in that it's an irrational number. It has a decimal expansion that goes on forever without repetition or termination. This other is base 10, which is the base of the number system that many societies in the world use. You can have logarithms of other bases, but these are the ones that you have commonly provided on your calculator. If you are working with logarithms in other bases, you can convert from one base to another, and we have a formula for that. This is known as the change of base formula. If you start with log base, we'll say b, and you're operating on some number a, you can create a fraction or a ratio that shows log to your new base, we're calling it d here, of the number you were operating on, and then the log of the same new base, d, to the base of the original base that you started with, and this will give you the same valuation as this one. So let's get a demonstration of that. We don't have a button for the log of base 2 here, but we can use this formula to convert this to something that we do have a button on our calculator for. Let's say we want to use the log base 10 option. we're going to write the new log here, and this is base 10. This is the LOG button on your calculator. We're going to put 5 up here, and then we're going to have log base 10 again of 2. And this, when you type that in your calculator, will have the same valuation as the original function that we had here that we didn't have a button on our calculator for. Let's talk about a couple other properties that are very nice that's going to return to us the multiplicative identity. The first example I have is log base 4 of 4. This is going to give us 1. Since the base is 4 and we are putting 4 into the function, this all goes to 1. The ln is, as I've mentioned earlier, a log base e. If we do natural log of e, this is the same as having this lower subscript that matches the number we're operating on, and this will also be 1. These can be useful things to have when problem solving. If you have something where you're solving for x and you have something that you've worked down to here, well, this evaluates out to just x because this becomes 1, and we have 1 times x will be x. So when you see this scenario in problem solving, you know that this is going to go to 1. Another useful property is where we can convert a product here into 2 separate logarithms. We're going to replicate the function of the same base and separate these factors into 2 separate logarithms. And instead of being separated by multiplication, they will be separated by addition. And this is biconditional. We could start with something like this and condense it into this, or we can start with something like this and expand it into this. We have something similar when it comes to a negative. If we would have a division step in here, which is the inverse operation of multiplication, we can separate this into 2 logarithms and have the inverse operation of addition. We would have subtraction. So we, again, are going to replicate the same log. The numerator is going to come out here first. The denominator is going to come out here and be the second logarithmic term that is subtracted from the first. Using this idea here as looking at a single logarithm function, if it's a negative function, we can rewrite this as, again, we're replicating the same function here, log base b in this case. And as we look going from here to here, this is the denominator. We can put this in the denominator and we can lose the negative. So that's an interesting technique that we can use that kind of is a piece of this property here. One of the most important and useful and common properties of logarithms is the ability to take something that has an exponent and pull it out in line with the rest of the equation. So this exponent of n can be pulled out and it becomes a scalar of the function. And this is another very useful property of logarithms that we can use in problem solving. If we have an understanding of the full equation of a logarithm, we can rewrite this as an exponential expression. The base here will be the base of an exponential expression. The y value over here will be the exponent, and then this independent variable will be the thing that this exponential is equivalent to. If we start with an exponential equation, we can rewrite it as a logarithmic function. One last thing that I want to look at is a simple example of how you would do a logarithm by hand if you have nice numbers. If you don't have nice numbers, I think you would probably be better off doing what most people do at this point and finding a calculator or a computer to help you compute these. But let's look at what happens here. I'm going to start with the log base 5 of 125. What is that going to be equal to? I'm going to start out and take the number here that we're operating on, and I'm going to divide it by the base. So 125 divided by 5 is 25. I'm going to take that and again divide it by the base. And I'm going to take that number again and divide it by the base. And now I am at 1, and that is where I stop. And I'm going to count up the number of times that I divided by the base, which is 3. So we have this, that the log base 5 of 125 is 5. Now remember, we can rewrite this as an exponential equation with the base here as the base, this number here as the exponent, and this is what that exponential is equal to. And you can do a quick check and verify that this is indeed true. So this, again, works with numbers that are easy to work with. If we have something that's not so easy to work with, it would be much harder to come up with this without some other more involved technique. Hopefully this has been helpful to help introduce you to the properties of logarithms. Cheerful calculations.